Welcome to my channel. In today's video, you are going to gain a deep understanding of the TCP/IP protocol foundations, and together we will write a TCP server from scratch, plus a health checker for network monitoring. If you already know about TCP and are only interested in the code implementations in Go, I have provided a timestamp for that, and you can skip the explanation if you want to. TCP, or Transmission Control Protocol, is the backbone of reliable data streaming between nodes in a network. If it was not for this protocol, we wouldn't have the internet today like it is. It's an important key in our daily digital interaction, from simple web browsing to complex cloud services. But before we dive into writing TCP code and establishing network connections, it's crucial to understand the process that ensures this reliability, the TCP handshake process, which sets the session for a smooth connection. Once we've covered the theory, we'll get our hands dirty and implement a TCP session in Go. We'll go over key operations such as dialing, listening, accepting client connections, and the proper way to handle session termination. Lastly, we'll implement a TCP health checker using only Golang and standard library packages. Let's get started. Before continuing, let me know in the comments below if you like this type of videos, and if you are interested in more of this. If you want any topic on this channel, feel free to comment and give me any feedback also. Share it with someone that you think this might be helpful with, and don't forget to leave it a like below. So why a TCP health checker? The number one reason is it ensures service availability. A TCP health checker is able to continuously verify if services like websites or databases, applications, and so on are online and reachable. If a service goes down, you'll know right away, ensuring minimal downtime. 2. Identifying networking issues early. It helps detect connection problems like high latency or packet loss. By catching these early, you can prevent performance issues from impacting your users. 3. Optimized troubleshooting. A TCP health checker gives you a clear insight into where the problem is, whether it's the network, the server, or another issue. This makes fixing problems faster. 4. Track network performance metrics. Measuring packet loss, latency, and response times provides key data to analyze the network's health. This helps optimize both speed and reliability. 5. Automate monitoring. You can automate the monitoring of critical infrastructure. This reduces the need for manual checks and alerts you immediately when something goes wrong. The number 6 reason would be support scaling infrastructure. So as systems grow, maintaining connectivity across multiple servers, nodes, and networks becomes harder. A health checker can help monitor and manage this complexity effectively. But what makes TCP so reliable? This protocol is so reliable because it can handle problems like packet loss or packets arriving out of order. This is something you won't get with a protocol like UDP, for example. One common mistake beginners often make is thinking that TCP solves all network issues, and that's not the case. Let's compare TCP with UDP. The UDP protocol allows us to keep the connection alive even if packets are lost and arrive in the wrong order. This might seem like a problem, but it's actually really helpful for certain types of applications. For example, live streaming or online games would struggle with too much delay if every lost packet had to be resent. With UDP, you can keep things moving smoothly, even if some data gets lost. TCP allows for reliable data sharing between nodes on a network. If it was not by TCP, we would not have things like web browsing, email, text messaging, file transfers, and even bank transactions, to name a few. So while UDP is better for speed in some cases, TCP is essential when data accuracy is critical. Let's talk about packet loss. This happens when data fails to reach its destination. typically because of data transmission errors like network congestion. Imagine trying to send 100 megabytes of data over a connection that only supports like 10 megabytes. The network would get overwhelmed and any extra data would get lost. This is called network congestion. And the nodes involved in the flow of the data drop the excess data, causing a data loss. TCP handles these issues by controlling the flow of data. It will adjust the speed of which data is sent, so it can send it as quickly as possible without losing too much along the way, even if the network gets slower. Like if your Wi-Fi signal weakens or your device you are communicating with becomes overloaded, TCP will slow down to ensure the data still arrives properly. This process is called flow control. But keep in mind that TCP is not magic. It can't fix a bad network or poor hardware. What it does is make the best out of the available network conditions by keeping track of the data being sent. If any data goes missing or unacknowledged packets, TCP will automatically resend it. Another neat trick TCP does is handling out of order packets. Sometimes because of how networks are built, packets of data don't always take the same path. And in a lot of cases because of routing protocols. This can lead to packets arriving at different times or in the wrong order. But don't worry, TCP rearranges everything so that data gets processed in the correct sequence. Together with flow control and retransmission, these properties allow TCP to overcome packet loss and make it easier to deliver data to the recipient. So as an engineer working with TCP, you have only to focus on the data you send and receive. Now let's learn a little bit more about TCP sessions. A TCP session allows you to deliver a stream of data of any size to a recipient. In most cases, the length of the stream will be determined by higher level protocols, and TCP will break this data into smaller packets or chunks to ensure reliable delivery. One of TCP's best features is getting confirmation when the data is received. This means you don't waste time sending large amounts of data only to find out later that something went wrong. But what happens if a packet gets lost? TCP uses timeouts to detect it. After sending off a packet, the sender starts a timer and puts that packet into a retransmission queue. If the timer runs out and the sender has not yet received the ACK from the recipient, it automatically resends the missing packet. You can think about the TCP session as a conversation between two nodes or devices. It starts with a greeting. The greeting is a three-way handshake. It then progresses into a conversation or data exchange. In this case, you won't have handshakes, but for each packet sent will be acknowledged. It must be acknowledged. And it then goes to the end of the conversation or the session. In this case, you will have a four-way handshake, which is the FIN, the ACK, FIN, and ACK. In Go, the NAT package handles most of the hard work, making it easier for you to manage network connections without the usual headaches. Now let's see how TCP establishes a session with the TCP handshake. The TCP handshake consists of a sequence of numbers, acknowledgements, retransmissions, and other features that sets the session for a smooth connection. The TCP handshake is like a greeting between nodes, in this case the client and the server, or the listening node and the dialing node. The TCP itself doesn't have a concept of client and server, but a session of two nodes. A TCP connection uses a three-way handshake to start the client to the server and the server to the client. Before it can establish a TCP session, the server must listen for incoming connections and waiting to react to them. So the server must be listening, okay, in order for the client to connect to them. And that's why servers are the listening node. The first step of the handshake is the client sends a packet with the synchronize or the SYN flag to the server. The SYN packet informs the server of the client's capabilities and preferred Windows settings for the rest of the conversation. The second step of the handshake is the server will respond with its own packet with both the acknowledgement or ACK and the SYN flag set. The ACK flag tells the client that the server acknowledges receipt of the client's SYN packet. The server's SYN packet tells the client what settings it's agreed to for the duration of the conversation. So the ACK will tell, okay, I received the SYN from client. The SYN will tell, this is the settings that we are agreed in our conversation. That's how we will handle the session. The third and final step of the handshake would be the client will reply with an ACK packet to acknowledge the server's SYN packet, completing the three-way handshake. By the completion of the three-way handshake process, it establishes the TCP session. And the nodes may then exchange data. As you can see here, it's established. They can now talk. They can exchange data, do whatever. And once a TCP session is set up, it stays open even if no data is being sent. But leaving a session idle for too long can waste memory. And there are great ways of dealing with that. There are great practices in the industry for dealing with that. When we start a TCP connection in Go, the program will either give you a connection object or an error. If you get the connection object, it means the TCP handshake or the setup process worked. The good news, you don't need to worry about handling the handshake yourself. Go takes care of it for you. Let's now talk about establishing a TCP connection with Go's standard library. Go's net package makes it easy to create servers and clients that uses TCP and even other protocols. But it's still important to handle connections properly. Our software should pay attention to incoming data and always try to close the connection cleanly when it's done, or gracefully if you want to. We are going to write a TCP server that will listen for incoming TCP connections, allow clients to connect, handle each connection in the background or asynchronously, exchange data between the server and the client, and close the connection gracefully. Establishing a TCP listener or server with Go's standard library is no big deal. To create a TCP server capable of listening for incoming connections, call it a listener, in Go we should use the net.listen function. There are other ones for this purpose, but this is the more generalist one. This function will return an object that implements the net.listener interface. Let's start by creating a listener or server. As you can see, as in the left hand side, the code is basically making a listener or a server. Let's understand the net.listen function in Go. So this function is how we start creating a TCP server in Go. It needs two things: a network type like TCP, TCP4 or TCP6 or even UDP. As you saw, I established a TCP listener or server. And the second parameter is an IP address and a port. These are combined as a single string separated by column, as you can see. If you don't specify a port, Golang will randomly choose a port for you. When you run net.listen, it gives you two things back: a listener object, this is the server, ready to receive connections, and an error, in case something went wrong. If it works, your server is now bound to the IP address and port you gave it. Binding means your operating system has locked the port for your server, and no other program or process can use it. If you try to use a port that's already in use, Go will throw an error. Always remember to close your listener when you are done with it. You can do this with the close method. It's a good habit to use defer to automatically close the listener when your function finishes, or a graceful shutdown if you want to. If you forget to close the listener, your program might run into problems like memory leaks or getting stuck waiting for a connection that will never come. And when you close the listener, any connections waiting to be accepted will also be unblocked and closed. What if you don't provide an IP or a port? If you don't provide an IP or a port, if you leave it empty or set to 0, Go will randomly pick a port for you, as I said previously. If you leave the IP empty, the server will listen on all available IP addresses. That includes both IPv4 and IPv6. To see what IP and port your listener ended up with, you can call the ADDR method on the listener. Let's see a little bit more about the network types. The network types can be TCP, TCP4, TCP6. It doesn't really matter. You can use UDP, you can use Unix, you can use a bunch of other protocols. The first argument of the net.listen in the network type, as we saw here, it's the network type, so TCP, TCP4, so on. The function will accept most protocols. However, let's talk more about TCP because that's the topic of today's video. TCP is the most common and works with both IPv4 and IPv6. If you want to use only IPv4, use TCP4 right here. You just have to write TCP4 right here to limit your server to only IPv4 addresses. You can use right here TCP6 to limit it to IPv6 addresses. Okay? Let's talk about how a listener or server can accept new TCP connections. In a real-world server, you will want to handle multiple connections at the same time, not just one, right? In Go, unless you want to accept only one connection, we use a for loop to keep the server accepting connections. Once a connection comes in, we handle it in a Go routine. A Go routine is Go's way of doing things in the background so that server can get back to accept new connections without waiting for the first one to finish. Let's talk about the process step by step. The first step is accepting connections. In this line, we are accepting connections. Inside the for loop, the server waits for a connection by using the accept method for the listener, on the listener. This method blocks or pauses until a client tries to connect and TCP handshake is completed. 2. Getting a connection. Once a client connects, accept returns two things: a connection object with type net.con that represents the link between the client and the server, or an error if something went wrong during the handshake or if the server stopped listening, and so on. 3. Handling the connection. We start a new Go routine to asynchronously handle the connection. This way, the server can keep the listening for new connections while it processes the current one in the background. So it can do some processing while it can handle new connections that's coming to the server. And 4. Closing the connection. After we are done interacting with the client, we need to call the close on the connection, right? This gracefully shut down the connection by sending a FIN packet. This tells the client the connection is done. Using Go routines lets us handle multiple clients simultaneously, taking advantages of Go's concurrency strengths. Without them, the server would get stuck waiting for each connection to finish before moving on to the next one, which would be really inefficient. Now that we understand how to make a TCP listener, let's implement it, and then let's make our TCP health checker too. Let's start creating our server or listener. Server, listener, okay. Package main, func main, okay. Let's leave it like that. So I'm gonna handle my TCP listener on a separate function, and I'm gonna call it TCP listener. You can call it TCP server, whatever. You can name whatever you want to. Net dot listen. Sure. So let's call the TCP 27.0.0.1 and port 321. Oh, you can even leave localhost or another address if you want to. No big deal. If there are any error with this, I want to return it. So I'm gonna call it net listen error, and I'm gonna return it. So yeah, now we have our listener. I'm gonna make a different function here so we can close the connection. You can just do defer listener dot close. You can do that too, but I'm not doing that here. So if our listener dot close, if our is not nil, I'm gonna return the error too, and I'm gonna specify really cleanly what the error is. Okay, so yeah, that's that. Sure. I'm gonna print where I'm listening to. This is the same code as you saw on the slides. That's nothing really different going on here. So yeah, right now we must handle new connections, accept new connections, right? And as we saw before, you need a for loop for that, unless you want to connect for in only one address, right? Or only one client. So we have a con, and we are gonna call inside our listener, we have the accept, which as you can see, accept waits for and returns the next connection to the listener. It's specified here, you know, that's here. Okay, so if we have any error right here, let's return the error, accept error. Okay, and I don't want this to return because I want to keep accepting new connections, so I'm just continuing, right? So okay, right here you handle or process the connection accepted, right? So you can do that right here, but what I'm gonna do a function to simulate some work, and I'm gonna call it, let's say, handle connection. This connection, this function must accept at least net.con, right? So we can do a little bit of with that. I'm gonna do that so I can track how many times the interaction took. And on my server, right here, I'm gonna make a different function so I can close just like that. Okay, so if or con dot close, if or it's not nil, I'm gonna log the error. Okay, no big deal with that. If I haven't received any error, but the connection was closed, I want to inform the address, the remote address that the connection was closed, and how many time it took in the interaction. So S, I think, yeah, and duration. So yeah. Yeah, and time dot since now. Okay, so we will catch it properly. Now let's log when we accept the connection. So connection accepted, processing it. So let's log that we accepted a connection from the remote address that we just accepted. And I'm gonna write to this client. As you can see, writes data to the connection. Write can be made to timeout and return an error after a fixed time limit. So, okay, this return an error receives a byte. Let's treat it properly. Sure, I don't want this int, but I do want to treat this error. Let's do that. If error equal, okay, con dot write error, sure, and let's call this function. So as we saw before, you must do that on a go routine or a semi-thread. A go routine is a semi-thread because when you are doing so, you are processing asynchronously, and a go routine is a lightweight semi-thread. Let's say like that, and I'm gonna call it, and I'm gonna pass the connection. So let's test this code. Sure, yeah, I need to call it. I'm pretty sure. Yeah, I haven't called it. Yeah. Yeah. Now we have our server or listener. Let's now build our Healthchecker, which will be on the client side. Okay, now let's build our Healthchecker, and I'm gonna make it on a separate folder, and yeah. Okay, so I'm gonna need a type, which will be a target. The target will have the IP, which will be of type net.ip, and the host too, which will be the type net.ip2, and the port, which will be an int, and the packet, which is the amount of packet that I want to send to my listener or to my server. I will also need a TCP checker struct. This struct will have target and for now only a timeout. Duration, sure. So right here you can have a bunch of things like TLS, verify, and so on. You can do a lot of things inside this struct, right? And I do want to have a result struct so I can handle my the results if it was successful or not, and also the message too. Success, which will be bool, the message, which will be a string. Sure. And I'm gonna use an function to correctly format the address for me. So yeah, TCP checker, this I'm gonna call it header, which will return a string, and this string will be only the address for me. No big deal. Sure. So .s, .e, the first one will be the IP as a string, and the second one will be a port. Okay, so yeah, pretty good so far. Right now, let's make our check function. And yeah, the check function, you can do a lot of things inside this function. Right now, I'm gonna pass a timeout, because this will allow me to pass inside the dial timeout and amount of time that I want to time out. If the connection is not successful, you'll see in under a second what I meant by that. So yes, we have this method called a dial timeout, which is basically the dial method that we saw right here. And no, we didn't saw it. But yeah, the dial timeout will help me create a dialer, which in this case is a client. In our case, in this case, we saw how to make a listener or a server. So this is the client or a dialer method. You can create a client using only dial, but we do want this dial timeout function, so we can use a timeout. Okay, so yeah, it's not a big deal. Let's specify TCP the address that we want to connect to, and if any error happens, I'm gonna return the result as I created it. So yeah, the success will be false, of course, because we have an error, right? And let's tell a message right here. I don't know, failed to connect, and the error, right? So yeah, I also want to different my connection. So graceful close connection. Okay, so I missed the message here. Okay, sure. So right here I'm gonna return success. So if it passes the error handling, we don't have any error successfully. So yeah, no big deal with that. And I'm gonna make a function to check with retries. It will receive a retries as an int retry delay, because we want to try again after an amount of time. And I want a logger here so I can log on my terminals to see correctly what's going on. And this will return a result for me. So yeah, this variable will hold the result for me, and I want to make a for loop for each retry, right? So yeah, let's do that. I want as we did in the client, in our client, in our server, in our listener, we are tracking the amount of time that the interaction took. So I want to track the amount of time that the interaction took in our Healthchecker. So yeah, you can have a good understanding on how much time it's taking to process things up and so on. So time.now. So result will be hc.check. So we are calling the check function with the timeout that we will pass. Let's calculate the duration of this thing. So start, yeah. And I'm gonna log dot write. So yeah, it receives a byte. And let's do it like that. Health check attempt, the number of the attempt, if it was a success or not. I also want to track the latency, which is, and a message. Yeah, why not? So yeah, I plus 1 result dot success. It will tell it if it was successful or not, and a result dot message. Yeah. And okay, inside this struct we have the success boolean property, and if it's somewhat successful, we are gonna return the result. Otherwise, we are gonna try again, right? If not successful, try again. Okay, so time.sleep and retry. So retry. try delay. Yeah. By the end of this function, we should return the result. And yeah, I think it's pretty much it. Let's now call it inside our main function. I'm gonna start so we actually forgot something. I need a way to make a new TCP checker. So yeah, let's do that. So let's make a new TCP checker, which will receive a net.ip. And what else do we have? A port, the number of packets, and this returns a TCP checker. Okay, this returns a TCP checker and target, which is target, and IP, which is IP, a port, which is port, and packets, which is packets, sure. And okay, now we can instantiate a new TCP checker. So let's do that. Let's parse the IP to this, and we are connected on this address as we saw before. So right here we need to pass the port, and the port is 4321 as we saw before. And the amount of packets, I'm gonna pass like 10 packets, which is the amount of the amount of packets that it will try to send. I will also specify a timeout for the check, and yeah. I need a log to call it. Let's do that. And the result. So the result right now, let me see what I'm passing here. So yeah, retries, retry delay, and the log. Yeah, sure. And check with retries. I'm gonna retry 5 times. I'm gonna have a delay of 2 seconds, and I'm gonna pass my log. Let's print the result here, and result dot message. So yeah, I think we're pretty much done with it. Let's go run TCP Healthchecker main.go. So successfully, as you can see, connection duration. So yeah, we can do one more thing here, which is, I think I'm sending a message here, and we haven't received this message anywhere. So let's treat that. I want a buffer, and let's make a buffer of an array of bytes or strings if you want. So inside this connection, we have a method which is called read. So read reads data from the connection. Read can be made to time out and return an error after a fixed time limit. So yeah, we can read data from that was sent over to us, and yeah, I think it's gonna work. But right here we need to treat an any specific error, because in the end of the file it will throw an error, but we don't want to. So I'm gonna filter that. I'm treating their errors like all the others, just to make it all the same. And if any error happens, I'm gonna log it and yeah, break it. So right now I want to print message, receive it, receive it, queue, and I'm gonna read from this buffer. Alright. This is the only thing we are doing on this check function. You can do literally an infinite amount of things. But yeah, let's see if this will work. Yeah, now as you can see, we receive it, the message. This is the latency. You can see that on server side it took like 100 nanoseconds, and right here it took like 600 seconds. We can try it again, and yeah. But now let's do a retry delay of like 4 seconds, and let's stop our server. Let's try it. It's failed, right? But now if you try again, if you start our server, it successfully is connected. So that's a simple way of doing that. There are many more things that you could implement on that, because there are a lot of things going on inside a network. But yeah, this code can give you like somewhat hint of what you could do or what you could build. And yeah, if you think this video was somewhat helpful for you, leave it a like below, leave it a comment, a feedback, share with someone that you think this will be helpful with, and thanks for watching.